Hi, today's lesson will be on interpreting the information that the periodic table can give us. Okay, so each element on the periodic table has two numbers. So, for example, I will choose one. Okay, for example, potassium, right? Okay, potassium. Look at the potassium. Potassium has a 19 above the symbol and a 39.1 also above the symbol. Okay, so the principal idea from this lecture is to analyze these numbers on potassium atom, for example. Okay, so okay, let's begin. This is very important to analyze this information that we have. So, okay, first of all, I will draw the box of the information we have for potassium atom, right? Okay, so let me see. Okay, there is potassium. Okay, at 19 and at 39.1, right? Okay, so that is the information about the periodic table and potassium. So first, look at this number over here. This will mean the atomic number, okay? The atomic number is represented by a C and is the number of protons, okay, inside the nucleus, okay? So that's very important. Number of protons inside the nucleus. Also is the position of the element on the periodic table. So potassium, okay, is in row number 4. And look at this. Potassium is before calcium, that is 20. And after argon, that is on the position number 18. So the number, the atomic number, will tell us the position of the element in the periodic table and also the number of protons inside the nucleus. Okay? So we have here protons, 19. Electrons around the nucleus also will be 19 because we are talking about a neutral atom, okay? So protons and electrons will be 19. So I have here a Mexican coin. I have here a nucleus, okay? And imagine I need to draw inside the nucleus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, 19 processes inside the nucleus. And of course that we need to draw also 19 electrons. Yeah, I know that it is complicated because electrons we need to add electrons, but also there are rules to complete energy levels around the nucleus. Okay, so the first two levels are circles, and we have four. After that, the energy level or the orbital change. Okay, now we have a ribbon. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now we have 12. So out after that, another circle. I will explain this when uh, the topic of electronic structure can be studied on this course. But now, just you have to believe this uh, from what I'm saying. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. 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 Yeah, I know. Um, really, I will explain this later. I just drawing atom very precisely. Okay. So that's it. I am drawing 18, yeah, 18 electrons around the nucleus. Okay. And of course, this number 39.1, okay, also has an information that can tell us this is the mass number. Okay, this is the mass number. And the mass number is the number of nucleons, right? Number of nucleons inside the nucleus. Okay, so nucleons, we have two particles here. Protons and electrons. No, sorry, no electrons, no, oh my God. Neutrons, okay? Protons and neutrons are nucleons, okay? So in this case, will be 39 nucleons on a potassium atom, right? And then we can calculate the number of neutrons applying a formula. Okay, so the number of neutrons will be, oh, I forgot, mass number can be represented by an A. So number of neutrons will be A, okay, minus C. Okay, A minus C. And then we have 39 minus 19, and that will be 20. So 20 neutrons will be the quantity for the potassium atom, right? 20 neutrons, 19 electrons, and 19 protons. That is the basic, information that we have here on the periodic table. So what happened? That is a neutral atom, okay? A neutral atom, okay, is an atom. I will hide this, okay? A neutral atom is an atom that has the number of protons equal to the number of electrons. Okay, so atoms are therefore neutral in their normal states. So for example, helium, okay, uh, analyzing the information that I give to you, helium has two protons inside the nucleus. That is the atomic number. Yeah. Okay. This guy over here will tell us two protons, two electrons because it's neutral. Okay. And neutrons will be 4 minus 2. That will be 2 also. Okay. A case of helium, for example. Okay. That is a neutral atom. If I, under some circumstances, the atom can lose or gain electrons, okay, they will not longer neutral, okay? Now we have a charge and that form an ion, okay? So I have here an animation, okay? This, for example, okay, first of all, there is no atom at this moment, okay? So I aggregate one proton. Okay, one proton will mean hydrogen. Remember that the number of protons will define which atom I am talking about. So if I aggregate another proton, that will be helium. Another one, lithium. Another one, beryllium. Another one, boron. Another one, carbon, nitrogen, oxygen, fluorine, neon. Okay, so first hydrogen. Yeah, at this particular moment we have an ion. Okay, because we have only one proton, and that means hydrogen. If I aggregate one electron, okay, we form a neutral atom. And yeah, of course, adding another electron will form an ion, but at this case, negative. Okay. If I continue adding another electron and another, okay, and another, yeah, there is a lot of blue balls. Each ball represents an electron. So, of course, it will be an ion, a very, very negative ion. Look at this, the net charge is -5, okay? It's -5 because this ball compensates with this orange ball, and then we have 1, 2, 3, 4, 5. So the net charge is going to be -5. If I again aggregate the hydrogen, so we have an ion positive, a positive ion. We can have, for example, lithium. Okay, I aggregate one. Sorry, I am adding one electron. Another one also is a positive ion, and adding another electron to the atom. That will form a neutral atom. Why? Because we have 1, 2, 3 electrons and 1, 2, 3 protons. Oh, okay. But if you look lithium at the periodic table, lithium has 3 protons, 3 electrons, and 4 neutrons, and the neutral form on the periodic table. Okay, so at this moment, right now, we have a lithium atom that is represented on the periodic table. Okay, Very good. Okay, so uh, ions can be formed by adding or removing electrons. Okay, if we have more protons than electrons, that will be a positive ion. If the quantity of electrons is equal to the quantity of protons, will be a neutral atom. And if I have more electrons than protons in an atom, that will form a negative ion. Okay, and look at the net charge in this case: -1, 0, or +1. Okay, because we have three protons here and only 2 electrons. Very good. So another example that will be a lithium atom on the neutral form. Okay, so ions, atom or group of atoms that bear one or more positive or negative electrical charges. Okay, positively charged ions are called cations. Okay, so for example, let's see, give me a moment. I will share my screen with you. Okay, there it is. Oh, okay, so positively charged ions are called cations. So this will be a cation. Okay, positive ion. Then negatively charged ions are called anions. Okay, and I will form an ion here. Okay, look at this. That is a neutral atom, and then we have a anion. We have an anion. An anion is a negative ion. Yeah. Okay, very good. So ions are formed by the addition of electrons or the removal of electrons from neutral atoms or molecules or other ions. So, case of lithium, right? Okay, lithium has 3 electrons, 3 protons, and 7 neutrons. Okay, so to form a positive ion, number of protons will be the same, number of neutrons will be the same, but in this case, we will only have 2 electrons going around the nucleus. Okay, so that will form a lithium plus and a cation. Okay, but otherwise, on oxygen, for example, okay, we have 8 protons, 8 electrons, and 8 neutrons. To form a negative ion, I will form negative ion, but in this case, -2, for example, okay? So we need to draw. We need to draw 2 electrons and first level energy, okay? 2 more on the second level, okay? And aggregate 2 ribbons, okay? Yeah, two ribbons. One, two, one, two, one, two, three, four, five, six, seven, eight. That's a neutral, but I am doing an anion, an anion, anion minus two. So we need to aggregate or add two more electrons. Okay, so that will be a minus two. Very good. Okay. Oh, of course, we need here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 8 electrons, sorry, 8 protons, 8 neutrons, and we'll have 10 electrons on this negative ion or negative oxygen ion. Okay, very good. So it's clear that we need to add or remove electrons to neutral atoms to form an ion. But what happens if we talk about isotopes? Okay, so isotopes are two or more types of atoms that have the same atomic number. So the number of protons in their nuclei will be the same, and position in the periodic table, but differ on nucleon numbers. That means mass number due to different number of neutrons. So in isotopes, the number that will change is the number of neutrons. So for example, element number 1 on the periodic table, that will be the hydrogen. Okay, hydrogen is an H with 1 and 1. So we have only one proton inside the nucleus and one electron going around. Okay, perfect. That is an hydrogen atom. Very good. So what happens if I aggregate a neutron? Okay, but the number of protons and electrons will not change. Okay, now I am doing an isotope, and it's called deuterium. Deuterium also will be an H, but in this case, 1 and 2 will be its number, because now we have one neutron inside the nucleus. And what happens if I aggregate not one, but two neutrons? And protons and electrons don't change. Oh, so I am doing another isotope. It's called tritium. It will represent an H, 1, 3. So look at this. The isotopes is the same atom, okay, for a particular element on the periodic table, but in this case, the number of neutrons will change, okay? And ions, the number of electrons is the change between a neutral or an ion. But isotopes have the same quantity of protons, same quantity of electrons, but differs on the number of neutrons, right? Okay. Um, Let me see. I can show you different isotopes applications, for example, for humans, and the use that we can have for different isotopes. For example, okay, let me see here. Oh, iodine 131. Okay, that isotope is used in diagnosis of a normal liver function, renal or kidney, okay, and blood flow, an urinary tract obstruction, for example, okay, okay, and we can use also iodine isotope, for example. Let me remember. I let me see. Um, Wait a moment. I am remembering. Mm, yeah, the the thyroid. Yeah, the thyroid. At the Spanish, the tiroides. Okay, the thyroid. The thyroid. We can use iodine on the thyroid to prevent cancer. Okay. Oh, look at this. The rhenium 188 is used to the beta irradiate coronary arteries from an angioplasty balloon. Okay. The cobalt 60, okay, and formerly used for external beam therapy, right? Um, oh yeah, the the iodine 131. There is an important information here about the half-life. What is the half-life? The half-life. Okay, each element or each isotope is radioactive. It's unstable. So for the case of iodine 131, it says 8 days. What is the meaning of these 8 days? Okay, so imagine that we have 1 kilogram of iodine 131. Okay, 1 kilogram. So if I wait 8 days long and come back to the source of radiation, after 8 days, I will find the half of the initial quantity that I had on iodine 131. So if I had 1 kilogram, 8 days later, I will have and a half of 1 kilogram. So 0.5 kilograms of iodine 131. Yeah, that's the meaning of the whole life. Okay. Of course, there are isotopes that have a very quick half-life period. For example, the krypton, okay, there are only 13 seconds on the half-life, okay? Or for example, I don't know, cobalt 60, there are 10 months, okay? There is a lot of time. And if I remember very well, uranium, okay, uranium that is used on the atomic bomb or the nuclear reactor, okay, uranium, okay, 235. The half time, let me search the half time. The half time of uranium 235 on the nuclear bombs of the nuclear reactor is about 700 million years. 700 million years. Can you imagine that? Okay, so that's the reason why we are always thinking on the different nuclear accidents, right? Because, for example, uranium 235, the half-life is 700 million of years. So if I have 1 kilogram of uranium 235, I will wait 700 millions of years to have the half of 1 kilogram of uranium 235. Yeah, that is a lot of time. Okay, so to finish, let me see. To finish, I will finish with the animation here, the application. Okay, so for example, lithium. Okay, lithium. If I aggregate another neutron, okay, nothing happened. If I aggregate another neutron, yeah, also there is an isotope there that is stable. Okay, I will aggregate. Okay, no, I will. Sorry, I am removing that. That's a neutral atom. Okay, if I aggregate one neutron more, okay, nothing happened. If I aggregate a lot of neutrons here, okay, that's unstable. Okay, that is a radioactive material, right? If I eliminate neutrons, okay, from lithium atom, so look at this. That's a stable atom of lithium. Yeah, 1, 2, 3, 4 neutrons, 3 protons, and 3 electrons. That's a neutral atom, and it's represented on the periodic table. If I aggregate a neutron here, that will form an unstable atom of lithium, right? Okay, that means the lithium will be radioactive. Okay. Very good. So that's it. Thank you. See you later.